Hello, and welcome to Ricardo's first webinar. Today, we're going to be discussing fuel cell, advantages, applications, and answers to today's mobility challenges. And we're going to particularly focus on medium and heavy-duty trucks. It's a different world we're facing today. We're doing this via a webinar. It's new to me. It may be new to some of you listening to this. I wish it was face-to-face. I wish we were all together, and maybe one day soon we will be doing that. But in the meantime, well, it's good to, and I'm excited to meet you all, at least in a virtual world. My name is Chris Brockbank, and I'm the Vice President of Technology and Strategy at Ricardo North America. Now, that may not be a North American accent you're saying, and that would be correct. I'm originally from England, and I've been spent 30 years in automotive, commercial vehicle, and a range of sectors, doing powertrain and vehicle integration. I've worked for Ricardo for a number of years now in the UK office, a stint in the German office, but I've been here in the US for about 6 years now, approximately 6 years. I'll be joined today by Rob Delcourt. Rob is our expert on hydrogen fuel cells. So Rob, would you like to introduce yourself and tell us, how did you get into hydrogen fuel cells?
Thank you, Chris, and welcome everyone. I'm Rob Delcourt. I've been working in the hydrogen fuel cell industry for over 20 years and successfully delivered projects in the heavy duty space in the US and the UK, as well as many other fuel cell power system and integration projects. And recently I just joined Ricardo, heading up their hydrogen fuel cell and technology strategy for the business, setting technology and initiatives for the direction. So it's a pleasure to be with you here today. And Chris, my journey started back in 2000, originally with hydrogenics, and working up in different areas of the technical side, project management, and business development, and then moved on down to San Diego, where I am here now, with a company that was called ISE Corporation, where my signature project there was the fuel cell buses for Transport for London, which ran from 2010 to recently. And then back again with hydrogenics. I've recently been the managing director, and now with Ricardo.
It just shows what a small world we live in. I've been on the buses you've developed before I even met you.
Fantastic.
So, what are the topics for today? We'll do a quick introduction to Ricardo to describe who we are and what we do. And then Rob will take us through the global hydrogen landscape, into hydrogen and fuel cell for power, before the optimization of fuel cell integration, a really key point, and finishing up with hydrogen at scale, a question many people are asking. So first, Ricardo. Ricardo is a global engineering and environmental consultancy, and we specialize in transport, energy, environment, and scarce natural resources, such as water. Our work goes across a range of sectors. Working at Ricardo is not a place that you're going to get bored or stuck in a rut doing the same thing. We could be working on passenger cars, commercial vehicles, rail, motorsport, and now into power generation. We're there and involved, and we're global in how we do it. But across everything, and in every assignment any one of us undertakes, we remain absolutely committed to the ethos of Sir Harry. So Sir Harry Ricardo is one of the most innovative engineers of our time, and he set out on a mission back in 1915 to maximize efficiency and eliminate waste, and that is something that is forefront to our minds in everything that we do. The company today has an ambition and a vision to create a world fit for the future. It's exciting. It's exciting to be part of. It's exciting to be able to contribute and deliver as a part of that. And we measure that via 6 key elements that you see on the screen there. And in fact, our talk today, our webinar, covers quite a few of them. Hydrogen fuel cells has an impact on air quality, on climate change, on energy sustainability, and clearly natural resource scarcity. So how big is Ricardo? Well, there's 3,000. There's 3,000 global engineers and scientists spread around the world, who are all committed to innovation. High proportion is in the UK, because that's where the company started. But we also have a number of locations here in the US, as you can see, on both the West Coast and the Midwest. Overall, we have 3,000 people in 51 sites in 20 countries. So what about Ricardo North America? What's our contribution to the vision that the company has? We're taking the word transport and changing it into mobility. Today, new mobility is almost in concept. It's not quite there. There's demonstrations, there's ideas, there's thoughts. We need to get to a point tomorrow, and it is tomorrow, when that new mobility is at scale. That's a chasm that we need to cross. We'll do it through design and development, but actually we're putting under 4 pillars. First one being advanced propulsion systems, and that's what we're discussing today with our hydrogen fuel cell. And that hydrogen fuel cell integration into the vehicle works with software and controls. As part of it, we need to manage the thermal aspects, and thermal is coming into everything that we do these days, be it main power source, be it the electronics that are running the systems. Thermal is becoming more and more important. And at the end of that, we will achieve our target, our new mobility for the future with zero carbon mobility. What's the phrase we keep in mind? We have to integrate that path to that better mobility future. So that's the company. That's what we're doing. And now let's dive deep into the main topic. So Rob, if you'd like to take us through and explain the hydrogen fuel cell world.
So thank you, Chris. In this section here, I'll talk about hydrogen fuel cell as a sustainable long-term solution for clean long-haul transportation. And it's important to realize that in order to have that sustainable long-term goal, there's many other factors that need to come together and work together here for that solution. Requires an ecosystem that covers the environmental policy and regulatory side, as well as a clear long-term vision on goals that will get us from here to 2030 targets in order to meet those CO2 emissions reductions goals. Of course, a holistic view around the vehicle itself and looking at the economics, the TCO analysis and trade-off of different technologies as well. And of course, the technical details around the engineering, the packaging of the components, the dimensioning, the challenges of the thermodynamics, and other things that I'll touch on here in the PowerPoint are all required to make the solution whole. So before we get into the technical part of the conversation, I want to talk briefly about the global hydrogen landscape. So let's start with the US. So some recent news has drawn a lot of attention is that CARB has adopted an advanced clean truck regulation that's just adopted a few days ago. So CARB's adopted a regulation that by 2024, manufacturers have to start selling zero emission trucks. And we're talking only a few years away here, but 4 years. Then by 2045, all trucks sold in California have to be zero emission. And then on top of that, we have another regulation, the Innovative Clean Transit Regulation, which also regulates public transit agencies and to help them gradually move towards 100% zero emission by 2040. So to facilitate that kind of a regulation, there's government funding in place that you can take advantage of. For example, there's various sources that are coming from CARB that are focused on vehicle side of deployments. The California Energy Commission is focused on infrastructure and deploying zero emission infrastructure, hydrogen infrastructure across California, as well as the FTA, which has also every year low-no funding, which is available that can help transit agencies with their goals as well. And recently, DOE has funding that's available, focusing on also R&D at lower technology readiness levels, and also some deployment projects at scale that can work together as sort of a mixed fleet and fuel deployment. Recently announced, the DOE has invested $100 million related to R&D funding, specifically in PEM fuel cell for heavy-duty long-haul trucks, as well as for deployment and development of large-scale electrolyzers to support large-scale deployments. So it's all about scale. It's all about getting there. In order to achieve goals, especially like the ones that California has laid out, to achieve 40% GHG reductions below 1990 levels and 80% below by 2050, this kind of approach is required. And of course, zooming out at a global scale, cities and organizations like the C40 cities are taking action to lay out climate action plans in order to reach global goals as well. Globally, there are two major global organizations that are promoting the hydrogen economy in the world. So one of them is the Hydrogen Council, the other one is the IPHE. Hydrogen Council is an organization that's comprised of 80 plus members. These are CEO-led groups and of companies that have invested heavily into hydrogen transportation technology, and these are also major global players. And according to the Hydrogen Business Council, 66 countries have already announced net zero emission targets by 2050 and are putting plans in place for a clear roadmap to get there. Other observations that have been made is that other factors that are help driving the adoption of hydrogen is the plummeting cost of renewables. That cost of renewables have come down 80% since 2010. Also, other factors in technology developments around electrolyzer. Electrolyzer capacity has increased by a factor of 55x since 2015, and also costs have come down as well too with respect to electrolyzer technology, and we're seeing more and more deployments at scale. So with a lot of investment that's going on globally here, some 30 plus major investments since 2017, there's a lot of momentum. It's clearly not slowing down. And the IPHE, on the other hand, is a global organization that it's not only representing some private representatives, but mostly this is the International Partnership for Hydrogen and Fuel Cells in the Economy, formed in 2003. This is an international government partnership currently consisting of 19 member countries and the European Commission. And recently they held a webinar emphasizing the importance of hydrogen and how it's at the center of many economic recovery plans, as well as getting to a decarbonized energy sector by 2050. So there's at this conference a lot of positive comments made about hydrogen, that it's the place to be for decades to come, that the cost of hydrogen is projected to fall, and even ahead of what analysts are predicting. There's that much momentum here that's moving forward. And of course, in order to get the cost down, we need to scale. So it's all about scale. And of course, hydrogen is at the center of many of these economic recovery plans, and hence can see as a way of getting us past the corona situation right now. Okay, so we talked a little bit about the global hydrogen landscape, and now we'll focus on why hydrogen for fuel cell and for power. We'll be focusing on trucks here. I mean, as the U.S. is a truck economy, goods are moved on a daily basis by trucks. So we'll start by looking at different fuels. Okay, so here in this slide, what I wanted to compare are different fuel technologies in terms of operation and commercial characteristics for mobility applications. So we're comparing these to diesel on the far left side of the heat map here. And everything on the left-hand side of the heat map is really non-zero emission type fuels. On the right-hand side, you have the battery electric and fuel cell, which is of the zero emission type. So in interpreting this heat map, with green being the most advantageous, and of course the red being least favorable, among the zero emission technologies, among the non-zero emission technologies, hybrid electric, plug-in hybrid electric offers some okay benefits, but with diesel offering benefits in other areas, but not quite being the reduced carbon emission profile. So diesel being an emitter of carbon. So in other words, in order to reach zero emission goals, the only choices that you have are really battery electric and fuel cell. And of course, with fuel cell, you have the benefits of long range, fast fueling times, a high payload capability, and of course, zero emissions across the board, and of course, the improved performance of fuel cell. A fuel cell can offer much greater performance. So that's why fuel cell provides overall a more balanced zero emission solution to mobility compared to all fuel types. Okay, so why hydrogen and fuel cells? So just to sum up some of the advantages here in one place. So hydrogen it's a proven power technology. It works, and it works wonderfully. It's already moving, buses are operating, moving goods. The technology works very, very well, and it offers an operation characteristic much like conventional vehicles, with having the benefits of also zero emission battery vehicles as well. As I mentioned earlier, it's fast fueling, so we're talking minutes to fuel your vehicle and redispatch the vehicle on its route, which can also have a benefit to operations in that it it has a positive effect in terms of the velocity of goods that are being moved. They can move a lot quickly as a result. And of course, there's no range limitation. And what this means, of course, is that a truck with a fast fuel capability can be turned around and meet its full range expectation on its duty cycle or planned route very quickly. And of course, very comparable power and torque. And this is the inherent benefit, of course, electric drive, offering even more torque than compared to a conventional diesel engine configuration here. So when you move up and you look at hydrogen as a fuel, it's a flexible, renewable fuel. It can be produced on site where the fueling station is, or even on site, sort of off site, through water electrolysis at scale and transported to the point of use. And of course, you can have a combination of solutions. A fleet operator who's running a fleet of zero emission fuel cell vehicles can have a combination of some on-site generation and at the same time bringing in renewable fuel from a dedicated renewable wind solar farm to make sure that you have the security of supply of your fuel and you're managing that chain for your operation. So it's a form of resiliency that can be looked at that way. It's also a sustainable zero emission well-to-wheel fuel. And if you're producing it by hydrogen, you can really, through electrolysis, have zero emission throughout the entire chain. But there's also added benefits of the hydrogen that go beyond the fuel. It can be used to store renewable energy. And coupling this with the variable dynamic of wind and solar, hydrogen can actually be used and banked and used at a later time as a form of energy storage for different applications. And of course, if you look at the climate, I talked earlier a little bit about ecosystem. There's the committed funding and investment that's going on, and we're seeing this everywhere. Significant government and private funds are being dedicated towards hydrogen projects as a way of bootstrapping economies. Investments are happening in the US, Europe, China, supporting fuel cell vehicles and their deployments. And most significantly, too, is the interest from private sector, which is important to have a fully working ecosystem, is that there's also substantial interest from renewable energy companies to invest in hydrogen and play a role, including even production through the form of hydrogen production farms. Okay, so like I said before here, that in the previous slide, compared to other technologies, hydrogen technology is the most balanced and advantageous zero emission solution for mobility. So it has been and can be applied to multiple market sectors, as you can see in the slide here, such as bus, truck, marine, and rail applications. And as I mentioned earlier, it's important to note that current government regulations have been moving in the direction of clean trucks, because trucks have been identified as the primary, highest NOx and emissions contributor. So given trucks' high utilization, trucks can actually consume the most hydrogen fuel compared to other transport mechanisms or modes. And this is also important because it stimulates hydrogen demand and also supply as well, and helps to bring down the total cost of ownership and lead in the mass adoption of hydrogen fuel mobility in all of these sectors. So in this economy, truck is basically the driver in this hydrogen economy. So we'll be focusing more on trucks in the remainder of this presentation. Okay, to give you more of a quantitative benchmark of the benefit of using hydrogen fuel, looking at this chart, hydrogen comparatively has a higher energy density than batteries when compared. But as you can see, out of all the fuel types on the left-hand side of this chart, that diesel offers the best energy density, but it's the worst polluter in terms of the highest emissions that come with it. So battery and fuel cell are only zero emission, but fuel cell, between those battery and fuel cell technologies, can give you the payload, long range, fast fueling benefits, and all those other performance requirements that will help you in your operations. So if you want zero emissions in your operations, a fuel cell is best for that solution. Okay, so as a result, of course, fuel cell can offer better payload compared to a battery vehicle when compared to diesel architecture. So really what we're seeing is as a fuel cell drive system is integrated into a vehicle, there's some savings that can be had in weight by reducing a battery pack and replacing that requirement for energy with hydrogen tanks and fuel system, and also replacing the power aspect with a fuel cell. the combination of fuel cell and tank system can offer weight savings that allows operators to carry more payload and deliver their missions compared to the diesel as a baseline. And of course, tracking technology developments and being technology leaders, we see a trajectory in improvements of overall weight of the fuel cell propulsion system, approaching parity with diesel over time. So significantly lighter compared to battery technology, and again, having the benefits of increased payload for delivering the needs of customer. So now we're going to move to a little bit more of the technical part of the presentation. I'll be talking here about the optimization of fuel cell integration. So far we've established that from zero emission perspective that fuel cell and hydrogen is a good candidate for heavy duty mobility applications. However, the right fuel still needs the right architecture in order to deliver the best performance for all applications. So there are many areas in fuel cell integration that we have to consider in order to optimize to do the correct design and putting a fuel cell propulsion system. And I want to bring up a few ones that are encountered mostly and most talked about in integrations. We'll touch on them here, and in subsequent webinars, we'll have a deeper discussion on other aspects of fuel cell integration. Okay, so this is a typical layout of a fuel cell drive system, and I'll just walk through some of the key components. A typical fuel cell propulsion system has a fuel storage, usually in the form of some kind of a vessel, hydrogen tanks, and valving stored at pressure, and that pressure allows the hydrogen to flow to the fuel cell stack as the fuel cell supply, which is used to make electricity inside the fuel cell stack. The fuel cell power system comprises of the fuel cell stack and other components such as the air delivery system, which drives air into the fuel cell. And fuel cells are like engines in that they are air breathing and require fuel to generate electricity. So that air system will delivers the airflow into the fuel cell. There's also a cooling system. Fuel cell stacks at higher power tend to be liquid cooled and have a cooling system and a fan assembly that's used to knock the heat out of the system with a pump to drive that flow. The fuel cell is usually connected to some form of interface electronics to a high voltage bus, and that could be a DC-DC converter or some form of bridging electronics, contactors, reverse current protection, pre-charge circuitry to interface that high voltage bus. And then moving down to the rest of the drive, we have the traction inverter, which drives the traction motor and ultimately is connected to the wheels of the vehicle. Heavy duty battery system, so the high voltage battery energy storage media, which is used for recuperation and acceleration benefit as well. And of course, power electronics for driving inverters, which power the accessories on a truck. In this case, where a power takeoff was used, we're replacing power steering and air brakes with an electric drive that require an inverter for that power. And then as we need to make up a low voltage power on the vehicle, we have power electronics for 12 and 24 volts for driving chassis related equipment. So all of this system here is controlled by a supervisory controller, which can interface to modules, subsystems and components in this overall architecture, and essentially is the powertrain controller for the vehicle. So this controller, as you see here, would interface with the chassis and take the driver inputs such as brake, acceleration, and other commands from the vehicle and pass it on to the drive system. So everything that we see here, I mean, these are the areas that we're looking at. We're looking at specifically the fuel cell system sizing and the energy storage sizing. When we're looking at the aspects of a design, we're looking at overall thermal management, sizing and packaging of the radiator for optimal layout. We're also looking at aspects of the electrical and mechanical layout. So the mechanical side, how we're packaging components, mounting for the application that they're going to be used in, such as heavy duty vehicles, where there's a lot of high vibration considerations as well. And then of course, on the electrical side, high voltage routing, low voltage conveyance for signal power and control signals, grounding, plumbing, all these things that make up the electrical aspect as well. And then of course, the controls and energy management aspect that are described here with the overall system controller, and of course interfacing with those details of the e-drive. So you need to do a lot of simulation for these components to work together. You don't just put the components together and hope for the best. You need to do a lot of engineering, simulation calculations to get the right design, the optimal design going forward. And of course, in Ricardo, we are very engineering focused and analytic focused in our approach. So in this approach, these are the example of fuel cell tools and system tools that we use. So we're applying these tools at our own proprietary workbench, and of course they interact with other third-party tools as well too. But we can design the overall system for feasibility. We can get right into and pick the components that are required for the fuel cell system at the stack level, component level, looking at optimal balance of plant components, and choosing the right pressure, flow, and voltage characteristics that will work with the system. And of course, at the system level, optimizing the overall control strategy with the packaging constraints at the system and subsystem component level as well too. Doing an optimization analysis as part of the workflow, and at the end coming up with an optimized hardware architecture that will work for the target vehicle. And of course, we don't just stop there. We take it a step further and integrate that work in a forward and backward mode, looking at the overall system design. So we're designing for specific applications such as heavy duty. We take all of the different duty cycles and drive schedules that are typical of the design, and of course do the optimizations that are required for energy management, performance, coupling that with the characteristics of a motor, a drive motor, and constraining it with some kind of optimization function. Could be cost or other parameters, but the output of this process is an optimized design that's balanced, tuned, properly integrated for the application at hand. And again, doing all by analysis. Okay, so before I continue, I just wanted to touch a little bit about power requirements at the wheels. This is one of the important characteristics for integrating this into a truck. When designing for heavy duty applications, it's important to realize that heavy duty vehicles are more demanding in their application. These are trucks that are higher utilization. They have a duty cycle with a lot of stop and go in their operation, coupled with low average speeds, higher average speeds. There's a lot of throughput in terms of energy between the energy storage system and the interaction of all the components in the fuel cell, depending on the architecture, could be operating at a very, very high dynamic. So it's not only that the duty cycle is important, which we talked about in the modeling framework in the previous slides, we also have to look at the conditions of gradability, which are important for a vehicle that's fully loaded, pulling at least 80,000 pounds. So slight changes in grade can actually translate to significant increases in traction power at the wheels. And because we're talking about a grade that could be a sustained, this is causing trucks to operate at a higher sustained peak power for longer periods of time under these conditions than they would in perhaps a lower utilization duty cycle. So this puts demands on not only the fuel cell system in terms of its dynamic and how we optimize its energy balance with thermal and control, but also power electronics and other components in the system. So it's an integrated, holistic view that's needed when we're looking at all these different design constraints, especially from the point of view of gradability. Okay, last but not least for architecture, just a quick recap for the audience who may be familiar with fuel cell architecture for trucks. There are two types that you'll hear about the most, and one is a prime mover configuration, where the fuel cell is larger, it operates more like an engine, and is characterized by a bigger fuel cell and smaller battery. So it'll have a higher dynamic, it'll ramp up and down much like an engine would. Another configuration is what we call a range extender configuration, characterized by a bigger battery, which has a combination of energy and power, and of course a smaller fuel cell, which may operate at a few steady state set points in order to maintain some control strategy around maintaining battery state of charge. So these are two common architectures driven by different constraints as part of the design problem, but they have very different operational characteristics. So we won't dwell on those differences in this presentation. We'll get more into those details in the next webinars, but certainly in both cases, the designing and packaging of the fuel cell, energy storage, the electric drive unit, and also fuel is important for not only weight balance and weight distribution, but accessibility, designing for manufacturing, for commercialization, and as well as serviceability. These are all key considerations when we're looking at the architecture of a fuel cell truck. And as I mentioned earlier, one of the most talked about topics in these days in this area is thermal management, and it's something that you cannot overlook in a fuel cell system. So by nature, a fuel cell is more efficient than an internal combustion engine in terms of heat dissipation. But one of the key challenges for thermal management is that fuel cells tend to operate at a lower temperature compared to internal combustion, which is also can be compounded by high ambient temperatures, making it a challenge for heat rejection at that level. So it's a very careful consideration that has to be made in the overall design, and we know how to do that. At the end of the day, I've always told my customers with my 20 years of vehicle integration experience that within the fuel cell, you have a microclimate that needs to be managed very, very carefully. It needs to be monitored and controlled. And in doing that, it allows you to maintain performance and durability of the fuel cell. So the better you monitor and control your thermals within the fuel cell, the longer it will last, and of course, the better its performance will be. So looking at the summary here, you get the idea that thermal management is key, but the fuel cell is not the only component in the system that requires thermal engineering and design by calculation and using the tools that I had mentioned earlier. The other aspects are, of course, the power electronics, the energy storage system, whether it's being air-cooled or liquid, the traction motor, transmission, all these other accessories require their thermal treatment as well and need to be considered in a holistic way when looking at the complete system here. So on the thermal side here, this slide just highlights that in a vehicle, you're going to have multiple cooling loops as part of your traction system, a propulsion system, that need to work together. Looking at this chart here on the left-hand side, you have essentially the power electronics and traction motor cooling loop, which comprises of a pump, a cooling media, plumbing, piping, and conveyance to a heat exchanger for that heat rejection. In the middle is a typical representative fuel cell loop with a fuel cell radiator and some other components as well too that could be tied into that loop, especially with a deionizer to help maintain proper conductivity of the cooling fluid itself, and evalving as required for proportional control of the coolant. And on the right-hand side is an example of a battery system that requires a combined heating and perhaps a cooling network in order to maintain operating limits. A chiller is shown here, but another possible configuration could be a water-air heat exchanger, depending on where the battery is being operated. But it's an important consideration to look at because batteries are one of those devices that have very tight tolerances on the control of temperature. They tend to be like people in many ways. If it's too hot, they don't work well, and if it's too cold, they don't work as well. So engineering is required to ensure good performance. But all of these loops here need to be balanced, and of course it depends on how you size the fuel cell, the sizing of the battery, the location of the cooling loop, and before you integrate, it's really important to look at everything, how it works inside the truck in a holistic view. So depending on how these all work together, other considerations need to be looked at. Now, serviceability, again, very, very important for people that will be tasked with making sure that these trucks are supported, how you run these pipings, how you actually prime cooling loops, location of pumps to ensure that priming is easy after a service cycle. And then, of course, other hydraulic aspects that are important, minimizing pressure drops, balancing the flow so that all the components are getting the flows that they need. So there's ways of simplifying the overall architecture, of course, and that goes all into the pre-integration engineering work that needs to be done to have a balanced design. So to give you a concrete example here, or just looking at these trucks as an example for the issues around cooling, all these trucks here have different cooling entrances depending on the geometry of the cab and the style of the vehicle. They all tend to be in the front of the vehicle and with maybe some side openings here, but this is where, depending on the shape of the cab and depending on how components are laid out internally, this is where your CFD, your computational fluid dynamics calculation can come into play, looking at the flow dynamics throughout the cab. So by performing an analysis and simulation in these factors, you can factor this into your thermal management planning. And it's not something that you would just put together in a vehicle and hope for the best performance. Mistakes can be very costly to fix on the back end. In this way, it's actually very, very important to do this pre-integration engineering work and use tools like Ricardo's CFD tools to tune your design for your operation. And one tricky part about thermal management to consider as well is when we're talking about sizing of the radiators. So there's some things to note. That looking at a project that we worked on, we had approximately 230 kilowatt fuel cell and did a quick summary here, but we did a calculation to show that we needed about 6.5 cubic meters per second of airflow to take that heat out. And of course, on top of that, we have to layer in other devices that we're trying to reject heat, so air compressor, other components, power electronics, as I showed on the previous slide. But in doing so, you have to take into account the electrical power budget that's required to drive the pumps and fans. And depending on how aggressive the cooling needs to be, you can have an additional 30 to 50 kilowatts of electrical power that needs to be planned for and how you're going to power that and what conveyance mechanisms for that electrical power are going to be used. So is this an approach? Is this true for every truck or the same for every truck? It's not the same formula. It needs to be designed according to the layout of the chassis and what the packaging constraints are. But the approach here is when you identify all of your components and you perform that analysis using the combinations of our tools to find that optimal size, you can get the radiator that is optimized for your vehicle. That's not too heavy, that it adds weight, not too large that it adds weight to your vehicle, but of course not too small that it underperforms and doesn't allow you to meet your performance targets. So designed in this way, it allows you to increase the durability of your fuel cell, and of course, with good thermal design and control, minimize that degradation of the fuel cell over time. And other aspects, just to highlight, here's some examples that I keep talking about, that using Ricardo CFD in order to help with the visualization and the flow. We can use the CFD software to look at where flow paths are running, eliminating stagnation zones, and of course ensuring that the components that need to be cooled can be done in this way. So again, as Ricardo, we can't stress enough that we want to make sure that the last thing you want to do is put together a design in a trial and error approach where iterations on repairs downstream may be required. Ideally, following this process here, this is an engineering approach. We're talking about the result being an educated build, so you know exactly what you're building before you build it. And just to take it up a notch, especially now with COVID, and given the situation that many of our design teams, we can't sit next to each other, Ricardo has a virtual reality platform for engineering design. So, if you think about the traditional approach to design review, where we'd be looking at 3D PowerPoints, maybe through a 2D screen, or interactive CAD session through 2D, you just really don't have that traditional spatial sense. But I'm sure you'll appreciate the full three-dimensional aspect here of the Ricardo VR platform. So imagine what this is here. You put on your headset. The truck that you're going to build is full scale, one-to-one size. It can be very, very detailed, and allows you to think about many considerations. So we talked about packaging and layout, but also get into servicing discussions. So it really allows you to ask your question, can I get this wrench in this area? Can I remove this component and even simulate the process of removing key components for serviceability? Can I access that nut, that bolt, and do a swift repair? So this allows you to not only do this with your colleagues that are co-located with you, but also remotely as well. So if you have offices that are elsewhere, UK, US, home, your colleagues are able to, and customers are able to interact with a full-scale design in this platform. So I mean, a lot of folks in overall design look over the detailed requirements for serviceability, and imagine all of the fights that could be saved by using a tool like this. And here's an example of what it looks like. This is a power generation application, but fully interactive, allowing detailed design reviews and instant changes of components as they appear here on the screen. So we didn't touch on all the topics in integration, but we did talk about most of the asked about aspects here. So in future webinars, we'll go deeper into other areas of fuel cell technology, of course, here. But before I conclude this presentation, I would just like to touch on the vision of hydrogen in the U.S. and its future, and talk about hydrogen at scale. Okay. So what you see here is the most talked about future of hydrogen. You know, hydrogen can really give you zero emission from well to wheel, and actually from well to power if you're utilizing renewable sources from energy that comes from wind and solar, and especially doing this at a very, very large scale, coupling it with water electrolysis. So the renewable hydrogen that's produced from electrolysis can be used in many different ways, not just as a fuel, but it can be stored in tanks for later use. It can be transported through a pipe infrastructure or network to its point of use, and it can be blended even with the existing natural gas infrastructure in a manner called power to gas, as an example of that as well too. But in this way, it can actually be serviced. It can be used to fuel all these different vehicles you see here in this mobility sectors: trucks, rail, marine, cranes. All these different applications can receive the hydrogen fuel, and as well as energy intensive sectors such as data centers as well too. So this is the scale that's going to bring down the cost of hydrogen to a significant level that's at par with conventional fuels. And at the same time, this is the mass adoption that's required that the US and global governments are pursuing to get hydrogen at scale. At the same time, growing fleets, so that supply and demand are occurring at the same time at scale, driving down costs and working towards the hydrogen economy. So this is the global vision that we see as Ricardo, and Ricardo, we play in every single part of it. Okay, we Ricardo, we're very proud to be the think tank of vehicle and propulsion engineering with major OEMs, vehicle OEMs, also using our expertise to bridge that technology capability into the future. So putting our 100 years of vehicle integration to work, and of course our expertise for zero emissions with hydrogen and fuel cells today is what we're very excited and committed to doing. Thank you very much. This concludes my presentation, and we'll now turn it over to questions.
We do have some questions. I'll start here, Rob, with one of them. Why only 2 stars for hydrogen refill time? Surely it's as quick as diesel.
Well, certainly we'll add more stars to the refill time. As I mentioned, that's just probably more of an editorial detail, but of course, hydrogen fueling time is quite quick. We're talking minutes. So absolutely, it should have more stars on that chart.
So what about pressures? Because there's a number of pressures that you can refuel with hydrogen.
So typically, we're talking in a truck where, so in a typical fleet type application, so it could be anywhere from 10 to 15 minutes, comparable to CNG, compressed natural gas fueling protocols. Truck comes in, you fuel quickly, and away you go. So this is, of course, a very important consideration when you're looking at a large number of fleets. If we're talking about trucks that are in the tens of 20s, the amount of time it takes to refuel, which hydrogen allows you to do in a short time comparison, is really critical for that cargo velocity, for being able to move goods quickly through the operation. So it actually helps with the scaling and operation efficiency of very large fleets, Chris.
Okay. Yeah, the question we were expecting, the 2 questions that we're expecting have come up. Availability of hydrogen.
Certainly. So, you know, hydrogen now, it's, I guess it'd be fair to say that, you know, hydrogen has actually been around for a while, and it's been moving to a place where it needs to be. There's already been funded programs, not only in the US, but globally, to build out hydrogen infrastructure, initially around light duty vehicles. But what's critical here is we should really talk about the cost of production. So if you look at the development in the last few years, I would say even the last 20 years, hydrogen has there's been technical developments that have been reducing costs in terms of performance improvements and getting to scale. We've seen electrolyzer performance increasing year over year from all of the manufacturers. And of course, this is closely linked with the cost of hydrogen production. So if we're talking about getting to scale, which is really what's needed, we need to increase both the supply and demand of hydrogen to drive that scale to get those costs down. And this is the direction that we're heading in right now. So think of the last 20 years as the time that we've been building on technology. From 2000 to about 2010, we've been making the technology work, improving its operation, planning demonstrations and getting it out there. And I was there in the early days and witnessing how the technology was evolving, having been involved very closely at the technical level. And then really the period of 2010 to now, we're looking at demonstrations where we're seeing government-funded demonstrations and more fleets that are coming out. So going forward, hydrogen is moving in the direction of increased availability. So really what needs to happen is that increased investment in infrastructure, increased investment in the technology to bring the cost down, getting to scale. And when we get to that scale, we can actually drive that supply and demand at the same time and building out. So it's all about those numbers and getting them out there.
And how is that moving forward at the moment? Because it's been discussed for many years. I'm seeing a lot of hydrogen refueling centers going in. There's talk with all the certain truck companies, new truck companies, about being able to cross America on hydrogen. How's that going? Let everyone know where we are in being able to drive and not have anxiety, range anxiety we talk about from the battery system, but not to have hydrogen range anxiety.
Right. So there's companies in the industry that are actually putting together fleets. We've heard about Nikola's recent announcements, and of course their plan to have fueling infrastructure along with their trucks, and similar models being talked about elsewhere to deploy hydrogen fueling stations very close to where fleets are being used. But what's important now, what's different now, is that if you look at the level of interest around the world, the hydrogen is at the core of even economic recovery plans and national plans to bootstrap economies and move things forward. And really what's key is to have that funding available to build out that infrastructure to do that. So if you go back, if you think about that slide I showed earlier with electrolysis being key, by funding that kind of a development, we can build large heavy duty stations at strategic locations across the company that could take advantage of wind and solar. Those stations can actually feed clusters of smaller stations that are also located in different areas within the state across the country that could be positioned to meet the needs of those fleets. And of course, if we're looking at applications very close to port type operations, you can have local stations. So very quickly you can see that hydrogen can actually couple all these different sectors, that we can have distributed generation and also strategically located fueling to make sure hydrogen gets needed to support hydrogen gets produced and delivered to locations where it is needed for different operation modes. So this could be rail, this could be heavy duty truck. And of course, this is what the DOE has been talking about with their H2 at scale, for being able to produce hydrogen in large quantities to service many different needs, to take care of that of other uses, not only in the energy sector and transport, but if we're talking specifically about transport in this case, having hydrogen available so that range anxiety and accessibility to these stations are very close. So it's part of that holistic view.
Okay, thank you for that. A few other questions. There's one here we had to clarify. I think we've got it. The question is, regard to commercial vehicle adoption for medium duty and heavy duty fleet owners, will it come first from BEV or natural gas vehicles? The question is yes. I think it's will be replaced. Which vehicles will fuel cell be replacing?
Okay, well that's a fair question here. So you have to look at the what are the benefits of the fuel cell vehicle compared to other technologies, of course. And if we look at a fuel cell vehicle, it has favorable characteristics. It can offer long range. So for a given amount of fuel that's stored on board, that goes back to the energy density on the vehicle. So this can actually replace a conventional diesel vehicle on that route and have that benefit of also zero emissions that go with it as well. It also payload capacity. I mean, a fuel cell propulsion system can be engineered in such a way that it's almost at weight parity or approaching weight parity with diesel, allowing for maximum payload capacity. So we're talking about replacing the conventional drive systems in vehicles where, especially in commercial heavy duty, where there's high utilization, a high duty cycle, maximum range is required, maximum flexibility in duty cycle and route flexibility is important as well too. Essentially, the operator needs to be able to deliver goods and operate their vehicle and sometimes unplanned routes. So having a centralized infrastructure or return to base model or access to infrastructure that would allow vehicles to fuel at any point on route is important. So we're talking about replacing vehicles and delivering flexibility, payload, range, and high performance as all of the factors that would influence, and of course, total cost of ownership of the vehicle as well.
Yeah, I mean, the cost is going to be a very important factor against deciding which one of those, and it's the slide you discussed about the relative cost coming down against batteries. It's going to be an interesting race to see who gets there first.
Of course.
Another question: fuel cells currently use platinum, which is expensive and rare. Can you comment on how you see this changing?
Yeah, so that's a great question too. So so platinum is a catalyst that's actually used at the membrane level of the stack, and that's designed to help the chemical reaction to produce electricity. One of the technology advancements that we've been seeing over the years is actually that reduction of platinum at the membrane level while maintaining performance of the fuel cell. So in early days, it was a higher loading, always a topic of discussion. Reducing that platinum loading over the years has been improving to the point now where the quantities of platinum inside a fuel cell stack are comparable to what you would find in an automotive catalytic converter, for example. And of course, there's new companies, startups, innovative companies that are working on alternatives to platinum as a catalyst, and this is a future development that we look forward to seeing in the industry as well. But the other side of things too is that if you look at the fuel cell and the recovery platinum, you can actually recover a large majority of the platinum that's in the system, up to 95%, with processes that have been established already in terms of recovering the platinum. And it doesn't just stop there. When you look at the fuel cell as a whole, all of the other materials within a fuel cell system can be recovered and recycled. So from a total life cycle point of view and a cost point of view, a recovery and environmental factor, there's a lot of benefits with the fuel cell that come to play here, not just around some key components.
So we've got the questions flowing in quick and fast at the moment. So let's see if we can get through some. Obviously, anyone who has sent a question in, we will answer them. We will send them to everyone afterwards, but we'll see how many we can get through here. $5 a kilo hydrogen is important to meet the cost of diesel. When are we going to get to $5 per kilo?
Yeah, so that's so cost is another great question, right?
Yeah.
So really, what's driving what's really driving that cost again is the ultimate goal, long-term goal. Really, we're looking at green hydrogen. Right now, hydrogen is produced from natural gas, and a lot of the processes that are there are driving today's cost. And when we're looking at longer term, we really need to get that cost of production down to levels that make it work. So, already if you look at around, say, if you do a quick calculation and you look around $8 a kilo of hydrogen, depending on the price of fuel, you're kind of at diesel parity. What will drive those costs down are the continued advancements in electrolyzer technology, which is the focus of a lot of funding plans in the EU, also with the DOE announcing a number of projects, not just the recent 100 million announcement that they made towards improving electrolyzer technology for large scale and heavy duty, but also other projects that they've been working on to deploy electrolyzers with wind, solar, nuclear assets as well too. So all these things will drive efficiencies in terms of the design, getting the cost down, and further bringing hydrogen down. The other aspect of this in looking at green hydrogen has been the falling cost of renewables, which is, the Hydrogen Council has pointed out as well too. And if you look at the other benefits, I mean, with hydrogen, with the renewable costs coming down, especially offshore electricity in other parts of the world coming down as well too, that further reduces the cost of hydrogen. So in general, you know, the Hydrogen Council has looked out and said that, you know, within the next 10 years, hydrogen costs can come down 50%. And that's even with some modest investments, incremental investments, which can make that happen as well too. So really it's driven by CapEx of the equipment, of course, electricity prices, and by getting to scale and with these investments, we'll certainly get there.
So we have a number of questions and we are out of time, so we will answer those. There's questions here about getting hydrogen to scale. There's a couple of questions about safety and hydrogen, which is quite common to cover. So we will answer those questions in return to you. And anyone who is watching this webinar as a catch-up, please email either Rob or myself, and we will any questions and we will come back to you. So the emails are coming up on the screen. So we're just coming to wrap up now. Thank you everyone for attending this webinar about fuel cell. There will be follow-up webinars from Ricardo, and the next one is actually on the screen. It's July 16th, Integrating a Path to Digital Transformation. And we will be discussing digital twin technologies. We will also, to follow up to this webinar, there will be further detail on fuel cell coming in the next few weeks, and we will be publicizing that. So as we're coming up to our time slot, I'd like to thank Rob for being part of this. I'd like to thank everyone for joining us, and I wish you a good day. Thank you very much.